Oh, alright. 9-4, USCMP 9-4, Quadratics and Projectiles. That's just your old basic, ax squared plus bx plus c, where a can't equal 0. Great, let's do it. Alright, well, so the book had this example where we took a ball and we threw it back and forth with a timer, but I got a chicken gun I want to use instead. Okay, well, got one loaded up in there. Straight up and bang. There she goes. Write this down, baby J. 1 second, 104 feet. 3 seconds, 156, she's turning around. 5 seconds, 80 feet. All right, well, what do we do with all of this? Well, luckily, Baby J left us some really good notes, so we can put those points into our calculator. You gotta remember how to do that from way back in the day, but we go to Stat, Edit, and then our X values of 1 second, 3 second, and 5 second we put into list 1, and then our height of 104 feet, 156 feet, and 80 feet we put into list 2. And then if you remember from chapter 9 back in the day, if we want to find a formula for that, we would go to Stat, and then we would go to Calc, and then we would go down to not a linear regression, but a quadratic regression, because we're working with a quadratic formula. Okay, hit enter. We get, can't really see that. Quadratic regression, remember we want it to say list 1, and then comma, list 2. And then we hit enter, and now we should come up with our formula, which of course is gonna be y, or our height, equals negative 16 x squared plus 90x plus 30. And then this is a wonderful, wonderful formula. If you were to dig into your book somewhere, you might find it as the general formula for the height of a projectile over time. Let h be the height in feet of a projectile launched with an initial upward velocity v, feet per second, and initial height of s feet. Then after t seconds, h equals negative 16 t squared plus vt plus s. Makes perfect sense, right? In other words, negative 16 is kind of our it's gravity. So normally we would say 9.811 meters per second, but we're gonna go with negative 16 feet per second here, and I think that has to do with like a coefficient of friction or air resistance. Then add our velocity times our time, and then this s is how high we are. So if we look at the formula from my chicken cannon, we have negative 16 x squared, so that's our dealing with gravity, because it's gonna go up, and then it's gonna pause, and it's gonna come back down with gravity. This 90x, that's the velocity of the cannon, or I'm sorry, the velocity of the chicken as it shoots. And then 30, that's the height of my deck. So I shot it from the second story of my house, which is 30 feet. Great, so now we know how to find that in our calculator. Amazing, wonderful. What if we want to draw a graph of that? Well, then we take this formula and we put it in. 16 x squared plus 90 x plus 30. Okay, so we want to adjust our window. X, remember, is our time. It looks like it probably ends at 6 seconds, so we can just say 10. Our Y, we don't really care about that as our height being a negative number, but we know that it goes up to about 200 feet. So if we graph that, we should get a nice curve there. We have our scatter plot on, so that's why these little dots are in here. Those are the 3 that we put into our stat function. And then look, there's our graph. That is amazing. So maybe another thing that we want to do is figure out where the top of the parabola is. And that would tell us, remember this is our velocity, slowing down. And then at a point it stops, and it stops moving upwards, and now it's going to move downward. So if we were to know the point where our direction changes and our height changes, then we would know the maximum height of this function, how high our little chicken got. So we would go to calc, so that was second trace or calc, and we would say maximum. And then it's this whole thing again. So left bound, we scroll over to the left side, say that's good. And then we find to the right of where we think it is, we'll say it's in there, and then we want to guess it's somewhere around here. And then it finds it, and it says our maximum is x equals 2.81 and y equals 156 point, we'll round up 6 seconds. So we know at the point 281 156.6 that the chicken has stopped moving and is going to turn down now. Got to a maximum height of 156.6 seconds, and it took it 2.81 seconds to get there, which goes along with the notes that Baby J took basketball. So 9-4, number 2. Use quadratic regression on your calculator to find an example for the parabola passing through the points 0, 6, 5, 3, and 10, 6. It looks like this. There we go. Okay, so how do we do that? Great question. First we turn on our calculator, and then we go to our stat. And then we say edit. And then we clear out these lists. And then we put in these other ones. 0, 5, 10. And then we go over to list 2 and we put in our y coordinates. 6, 30, and 6. If we look at those points, we can probably see that, hey, the parabola is moving up, and then at some point it comes back down. Okay, so it says use quadratic regression on your calculator to find an equation for the parabola passing through those points. Great, so we need to go to stat, we go over to calc, and then we go down to quadratic regression 5. And then we have to put in our list. So second, can't see that. Oh, old people in technology. Okay, so second, list 1, comma, list 2. And then we hit enter. And then that gives us our answer. So we write that down in our notebook so that I can give you a grade. Okay, so y equals negative 0.96x squared plus 9.6x plus c. And by c, I mean 6. Silly. Okay, there's number 2. So nice. 3. A ball is thrown from an initial height of 5 feet with an initial upward velocity of 30 feet per second. A. Write a function describing the height of the ball after t seconds. Oh my goodness, how will we ever do that? Oh, it's right here in the general formula for the height of a projectile over time. Or h equals negative 16t squared plus vt plus s. Everything we need is right there. Okay, so we need to write that function. A. Okay, so negative 16t squared, that was gravity, plus our velocity was 30 feet per second, 30d plus s, which was our initial height of 5 feet. Wonderful, just amazing. Okay, part B, how high will the ball be 2 seconds after it's thrown? Well, that's a great question. Thank you, USCMP, for asking us that. We can either plug in 2 seconds for these t's and do the math that way, or we can have calculator do it for us. So let's have calculator do it for us. Clear out y sub 1 equals negative 16x squared plus 30x plus 5. And then we would make a table of it. And then we would go to 2 seconds, and it will be 1 whopping foot high. Oh my goodness. Okay, and then part C, what is the maximum height of the ball? Well, I'm glad you asked. It could be 1 second at 19 feet, but probably not. Why don't we graph this bad mamma jamma? Giraffe it. Say this is -1. This is -1. Graph it now. Boom, okay. So, we want to find the maximum height, which is going to be at the maximum point on the parabola. So we go to second calc and we say maximum. And then we do the left bound, right bound. We take a guess in the center, around there. And it says our maximum is at 0.9374 and a y value of 19 feet. So it was pretty close to 1 foot and 19 feet. So see, what is the maximum height of the ball? It is 19 feet. That's amazing. Good job, everyone. Okay, number 5. Woo! We are plugging along here. Okay. 5. An object is dropped from an initial height of 40 feet. What is the object's initial velocity? What is its maximum height? Well, that's a great question. Its initial velocity is going to be 0. It is not moving when you drop it. For a second, it just hangs out there. Does that make sense? Like I dropped this pen. It's like it didn't start moving instantly. It took it just a very, very small amount of time to get going. I think. That's probably right. Okay, so 5A. What is the object's initial velocity? Velocity is 0. Or you could say 0 feet per second squared. What is its maximum height? Well, if it starts at 40 feet and then it falls to the ground, it cannot get any higher than 40 feet. So max is 40 feet. Great. Write a formula for the height in feet of the object after t seconds. Okay, we can do that. B. Write a formula for the height in feet of the object after t seconds. How do you think we do that? Well, we probably do this negative 16t squared plus an initial velocity of 0 times t plus our initial height, which was 40. Does this part make sense? 0 t. That second part is its initial velocity. It was not moving when it started. So we just have the force of gravity acting on that 40 feet. Okay, so our formula would be height, which is our y or h, whatever you want to call it, equals negative 16t squared plus 40. Thumbs up, America. Okay. C. After how many seconds does the object hit the ground? Well, so once it hits the ground, our height or our y is going to be 0. So we can set that to 0. So 0 equals negative 16t plus 40. Now we got to do some y equals mx plus b in here. So what do we do first? Yep, we subtract the 40 from both sides. Great. Negative 40 equals negative 16 squared. Then we do a little Kyle step in there. I can't say his last name because I'm putting this online. You guys are not 18. So it's the Kyle step, not the you know what step. Okay, so come on, computer. Got 40. And we gotta divide that by 16. Technically it's negative 40 divided by negative 16, but the negatives cancel out, so I'm not gonna do it. 40 divided by 16 equals 2.5 equals t squared, and then we would take the square root of both of those. So we say, hey, computer, what's the square root of 2.5? And then it would be t equals 1.58 seconds. Okay, so at 1.58 seconds, the ball has hit the ground. Technically, it could be negative 1.58 seconds, but we're gonna drop that negative because it's too confusing. And I don't want it. I don't want it. It's too sunny in here, guys. Okay, question 9. A small rocket is shot from the edge of a cliff. So exciting. Suppose that after X seconds, the rocket is Y meters above the cliff, where Y equals 25X minus 5X squared. Great. We're gonna graph this equation using the window that they say there. Okay. Well, I don't mind doing that. Not at all. They've done all the hard work for me. Okay, Y equals 25. X minus 5X squared. So notice that they put this X squared after the X, but it's still negative. Gravity is affecting it. Okay, so we're graphing this with the window that they set out for us of 0, 8, -5, and 40. We graph that. And there it is. Oh my goodness, so beautiful. Got this little point in here, which is just our scatter plot. So we can take that off if you want. Plot. Off. Graph. Okay, there we go. Wonderful. Okay, so there it is. B, what is the greatest height the rocket reaches? Well, that would be right here, wouldn't it? How do we do that again? That's right, we go second, calc, max, left bound, right bound, and there it is. 2.5 and 31. Okay, part C, how far above the edge of the cliff is the rocket after 4 seconds? Well, great question. If we go to a table, we can see how far it is at all of our seconds. So at 4 seconds, it is 20 feet off the ground, off the cliff. D, between which times is the rocket more than 20 feet above the cliff's edge? Well, looks like that happens between 1 second and 4 seconds. At 1 second it's at 20 feet, and at 4 seconds it's at 20 feet. And in between that, it is above that. What is the height of the rocket after 6 seconds? -30 feet. So what does that mean, right? It's on a cliff, you shoot it, and then it's like, woo, 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 oh, but then it can go below the cliff. So at 6 seconds, it's dropped 30 feet below the cliff. And last and least, for me anyways, you guys have more problems. F, at approximately what time does the rocket fall below the height of the cliff's edge? So we're gonna say that the cliff's edge is 0 on our Y scale. And that happens when our X is 5. So at 5 seconds, it is at the level of the cliff. Anything below that, it is, or rather, anything after 5 seconds, it should be below the edge of the cliff. So at what time does the rocket fall below the height of the cliff's edge? At 5 seconds. Okay, I'm done here. You guys do 1 through 10.